Next speaker today is Luis Suarez. The title of his talk is AI-powered water treatment, engineering sustainable and circular solutions for the next generation. Luis is a senior process and specialty engineer with 25 years plus experience in sustainability-driven water, wastewater, and utilities for LNG, refining, and petrochemical facilities. Educated with a BS in chemical engineering at USB and graduate studies at UCAB. He serves as Houston Lead Process Engineer, Utilities and Water, SME, leading pre-feed and feed across offshore LNG facilities, MBR-RO, and reliability and sustainability programs for Aramco, SABIC, ExxonMobil, and Phillips 66.
Okay, thank you so much. Probably this topic has too many things or too many angles to see and to discuss with the data centers today. I will try to summarize the most important key factors that we have to keep in mind, the new generation of engineers, because we have to run or try to catch up the same speed as the AI is growing. So I want to try to summarize the most important key design aspect. So I will start my presentation with a question for you. How many of you has having the curiosity to put your hands in the top of the fan that is in the AC outside of your houses? Okay. So how do you feel when you put the hands there? It's hot, right? So this is a principle that basically this fan, the AC that you have in your houses, is taking the heat that is inside and is taken away to cool down the house. Correct? So going a little bit on the scale, let's see that this is a simple way when we can say that we have air cooling system in your houses. So you don't have a cooling tower to cool down your houses. You have just the heat inside, and we have a refrigerant that is changing the heat and cooling the temperature for the air that is coming in again. Correct? Mm. Let's go to the case of the car. In the car, we have two sources of heat. One is in the cabin, when we are depending on the people, the heat can be generated more or less. And we have another source in the engine. So the cabin is taken out in the same way, more or less, that we have in our houses. But in the engine is a different story. First, because the heat is more than the heat that is generated by human being. And second one, the engine to be working in optimized level needs to take the heat from the source. So that's why we have a circular system with a fan taking through the radiator, when we can say that we have some type of cooling the engine with liquid cooling. So with this in mind, I want to, with this simple idea, the generation of the AI has been generating a massive and accelerated construction of data centers. Yeah. That normally those data centers are compounded by massive racks of trains of rack that they are supporting the technology that we are using today. So what is the reason of the high consumption of water and heat of those systems? The first one is that when we have, going again to the case of the house, imagine that the data centers at the beginning, the traditional data centers that we used to know, are equivalent to the house when we have 10 people. So, but what happened is instead of have 10 people, we increase this to 1,000 people in the same space. So obviously the heat regeneration inside is going to be probably 10 more times, and progressive in the time is going to be, we will face a inflection point when the air, the cooling the space by air is not going to be enough. So that's why engineers start optimizing the system first with the air cooling and putting heat exchangers in the rear heat exchangers or chillers or another system. But with the increasing of the AI apps and the racks and the densities, we cross the limit when the air cooling is not enough. That's why we need to consider another techniques to cool and to recover the heat when it's when the cooling system getting the way. But not everything stopped there. The thing is, with the increasing of the chip technologies, actually we have, going to this table, the chips has been, actually the new generation of chips are more powerful and generate heat like 10 more times compared with the chips in the past. So as you see here, okay. This is to have an idea, the large model that are growing in exceptional fast pace has generated the power consumption. This is in 2016 to have an idea. This used to be 250 kilowatts. And actually, in 2024 to 2025, we are talking about the chips is the power generation is around 1,200 kilowatts. 300, yes, this is kilowatt, not watts. So this is just this graphic is just telling about the GPUs that you can check in the. Sorry for the people online. I'm going to make available online the terms, the list of terms that I said. But for the graphic power units and the for using in the large models, that's produce a thermal design power that is, if you see compared with 2016 and compared with 24, 25 is more than 4 times. So that's why this is the main reason why these data centers that, for me, by the way, data centers is not the right, in my opinion, it's not the right term, because this is like a powerful supercomputers that we are right now. And data centers used to be some places when we control the data and has later a small consumption for rack compared with this micro supercomputers that we have right now. But anyway, this is my opinion. So another important thing is that which is has been driven this massive construction of data centers, is that the AI is not anymore available for a few groups like a government or another, or just for science. Now AI is commercial. So with this going to commercial mode, actually we have proliferation of too many apps that has been creating the massive the massive growing for the construction of this data center, because all those apps that actually we saw has to be supported by the rack that are including the data centers. So another important thing is that all those chips, and another difference we compare with traditional data centers is that those chips has the capacity to work in normal mode for more than 90% of the capacity. Compared with in the past, as I say, the legacy data center used to be designed to work at 10%, 20% capacity, up to maximum of 50%. But this is another important factor that is involved in the power generation of the system. So just to have an idea, this is in US only, just the consumption of water related to data center, it was around 17.4 billion gallons. So imagine, I don't know how many rivers we can quantify in this amount of water that has been using, and this number or this data is for 2023. Imagine that we are in 2026, how has been the increasing in this. So this is complementing my comment about the density for each system, how has been growing, conforming with the growing of technology, and what is the best cooling approach or the optimization, how has been growing and increasing during the time. So as you can see here, let me see again that how you are better than me. Okay. As you see, let's see the legacy enterprise. It was the data centers, the traditional, with the consumption used to be less than 10 kilowatts per rack. And that used to be the air or the cooling used to be with conventional air. So the throttling risk, which is another important point because those data centers has to work 24/7. They cannot stop the service in any time. That at this time, to control the temperature inside the racks, the risk used to be low just using conventional air. But as you can see here, with the growing in the CPU and GPU units in the racks, the density start moving to 20 or 30 kilowatts per rack, the generation. So that in that moment, one of the optimization, it was air conditioning with real, this is real heat changers and partial liquid. And this is when the DLC was needing more than 20 kilowatts, 20 kilowatts in energy. So the AI, when the AI appeared, the generation started growing, increasing to 40 to 80 kilowatts per rack. So it was when another technology, it was the air, it wasn't enough to cooling the system. So it was the new technology that is called direct liquid to chip. It was incorporated to cooling as a cooling technology to face the problem and try to lower the risk of the heat inside the racks. And finally, when we are actually right now, is with generation more than 100 kilowatts per rack. And definitely in these cases, actually, to lower the risk of throttling the units, the heat has to be recovered using liquid system, a combination of liquid system plus air system, because it's not enough. So, in line with the explanation before, all the system has creating problems in the has environmental impact, and one of the impact is based as you say before, Nika, for increasing energy consumption. And another important point that we have to keep in mind when we are designing and trying to keep the vision of the in the sustainability view is that the throttling performance has to be minimized. So there is a list of mitigation strategies. For example, in the case to minimize impact in the environment is procure cleaner power. Let's see, the source of power could be solar, could be air, could be from the wind. But actually too many of these technologies are improving. But in general, the idea is try to find the way to produce power with green energies. This is one of the possible. Improve the power efficiency. I want to explain later about this. Reduce the water usage efficiency. Mitigation strategies is one of the possible strategies to optimize the heat recovery is transition from the direct liquid to chip using water to immersion system that actually probably some of you has been hearing as a dielectric fluid that are in contact, and when they are in contact with the heat just evaporate. So we have a change of phase and the gas is recovered and pass through a condensate to becomes liquid again. But the advantage of this is the minimize the use of water or eliminate. But this is there is too many ways to cooling the racks, different technologies. So I don't want to go deeper in this. Just show the holistic design that has to be considered to optimize those systems. This is another mitigation strategy just to throttle the performance, but this is just thinking in the point of view of somebody that is his problem is just the data center, is ensure that the cooling the distribution unit that are here. Sorry. That one, that has to be redundancy. It's important to know, probably some of you know that the system has to warranty the service 24/7. So interruption of the service is not allowed. That every system, the supply of power, the cooling everything has to have a backup, because there is not allowed just by design that to get out of service. So too many of these, especially the redundancy, is one of the most important factors that has to be considered in the design of the data centers. So the ideal world, or the ideal that we had to thinking in the sustainability. I create this graphic that we move from the only cooling using air to the other just cooling using water, and the combination of both. So as you can see here, of course, we move from, this is the only air. As you can see here, the energy consumption, of course, if you use only air to cooling and space, is more energy. So it's more energy, but it's less water. This is the other extreme, just liquid plus air, which is the ideal combination. It's a balance between how much energy we are reducing and how much water we are optimizing to cool in the same space. This is the other extreme. Maximum, of course, cooling with water is more efficient than cooling with air only. But the drawback of here is this low energy, but the consumption of water is bigger. So this is more or less when we are deciding to stay just in the middle, try to make a balance between energy and water consumption. So this is in general the idea of this graphic. So one of the important terms, or the most important terms that has to be considered, is the power usage. That is the total energy in the facility, using not only for the IT, it's in general for the whole system involved in the data center, and the water usage. So how much water, this is a measure of the efficiency of how much water is used to cool down a unit of IT by IT energy, by the heat generated by IT units. So another important factor is the water usage source, because as you previously mentioned it very well, is that the water usage is not only the water usage for the cooling the system. We have water indirectly used to produce the power. So all those factors has to be considered in our design. So to have an idea, this is going little back with the simple idea at the beginning of the car and the house. Originally, they used to be this used to be the traditional way to cooling the system, just using air. So normally, we used to have a heat exchanger in the back, a plenum. When the cold air is coming, is sending through the front of the rack, and the hot air, the hot exhaust, is taken by probably by a duct or some fan to send it back to the cooling unit. So in the optimization, during when the heat started increasing because of the increasing in the density of the rack, some optimization start putting in place. For example, like isolate. This is it's called like a core ale, to avoid the mixing with hot air with cold air, for example. That was an optimization. And normally the heat changer, the rear heat changer, it was calling close to the source of the heat. So that was some type of strategies to minimize and to optimize the heat recovery using only air. But when the air system is not enough, this is the second drawing here is just when the heat is not enough and we need to recover the heat using just air. There is another system using, for example, chillers here, which is another optimization because of the increasing in capacity of the heat. But when it's not enough, we need to go to the water or combination of water and air heat recovery, which is the next system. So as you can see here, This is a combination. Here you can see we have air that is cooling and the heat is recovered. And this is using liquid, direct liquid to the chip is just this. This is the explanation. The liquid is sent directly inside the rack. And the heat is recovered just from the source, which is more, it's an optimization. But additionally, there is an remaining heat that has to be recovered by the air because the liquid is not enough. So you have there an example of combination of air and liquid, which is, by the way, this is actually the way of the next generation of data centers are cooling the massive heat that they are generating. And this is just liquid. As I said, liquid to the heat recovery using only liquid to the chip is that the cold water is sent directly to the rack and the hot water is collected back. And we have two separate loops. This is internal loop, which is in the cooling destination, the cooling distribution unit, and the external loop is connected probably with a cooling tower that is on the top of the building or something like that. So this is more or less the idea of the cooling using combination between air and water. So why all of this is important? First is because we need to, my intention today is create a conscience in all of you, because I think directly or indirectly we are involved in the design of too many systems. And it's important to understand the interaction and guarantee a sustainability future, because the growing of AI and all the data center is not going to stop. It's going to evolve. So definitely, if we want to preserve our resources and try to have a sustainability digital future, we need to consider how the interaction between all those factors involved in the data centers and the power and the water and the resource that we have in our environment has to be combined together in an holistic design. So we have too many, as you can see here, we have this is just recommendations that I has been putting based on my investigation. So for example, the cooling for those systems in the future has to be considered using reclaimed water, which is tertiary water, because it's water that is already contaminated, has to be already treated in wastewater treatment plant. Why we don't reuse this and force the new generation of data centers that they had to use only this water? This is an idea. Industrial reuse. Normally, more of these data centers are very close in industrial zone. When we have industrial water produced, storm water, seawater or brackish water would be the source. The last, if we don't have any alternative, is potable water, but definitely has to be the last resort to evaluate in the hierarchy of the sources of water to be used by for cooling. Second one, the treatment trains. The treatment trains, especially for the water produced by those systems or the water that is coming from the cooling towers, we have too many alternatives, which is, oh, 2 minutes. Oh my goodness. Okay, this is another alternative, and brine minimization. If we are using reverse osmosis system, because the seawater is the major source available. Definitely, brine minimization is one of the things that we have to consider. So, okay, I think this is the most important part in the presentation, or the message that I want to leave with you guys. The data center, or all explanation that I have been doing so far, is around the data center. But it's important for us to consider that the data center needs supply energy. The data center needs water from the cooling. And this is the cooling water is coming from, could be for two sources. One is for the reclaimed water, and the other one is for the cooling towers coming in. But it's important for us that we have to make the design sustainable. That means that we need to change the vision of the data center to be the vision that actually everybody has, is that those systems are monsters that are angry and thirsty. They are consuming energy and water in massive measure. So we need to change, or put the design to change the vision that those units has to be social asset. What I mean with social asset, that this unit has to produce energy to pay back to the society that is around, and to produce water it's like the payback for the environment. So, for example, the cooling towers, you can see here, the blowdown of this cooling tower can be combined, it can be sent to the wastewater treatment plant, and this water, this street water can be sent again to the data center, and the energy, the massive heat recover, can be sent back, power return, to help for example, to heating to many systems to produce power. So that could help to minimize the carbon consumption, and additionally, it's a payback to the neighbors and the community that are around. So it's important for us to make it's our responsibility to make this whole circle sustainable, to allow the growing of the technology, but preserve the environment and preserve our resources for the next generation. Sorry for the extension. I want to send, I think I prepare for you guys, but I want to share online. It's like let me show my design playbook. So in this design playbook, I put like a step by step, what is the factors that has to be considered instead of the source of the water, the cooling system that has to be used, the purpose that we have to have in the mind when we are designing a system like that, circularity beyond water. So we need to set the KPIs. That is important to keep the right balance between water and energy, and is in the most important thing, community engagement. Thank you so much. I want to close my presentation to this little message: save water, save life. Thank you so much.